Hello everyone, this is Moshami. Today we are going to discuss kinematics but from the calculus point of view. So we have already talked about kinematics in AP Physics 1 where you get all details regarding the theory, but this is just an addition to include calculus into kinematics. So these are the topics which we have discussed here. Let's start with the definition of the initial parameters which are important. Instantaneous velocity. So instantaneous velocity is nothing but the velocity of the particle at any particular instant of time. So when we are trying to look at it from the calculus point of view, this is how we can define or we can write down a mathematical form for the instantaneous velocity. So instantaneous velocity v of t can be written as limit delta t tending to 0, delta x, delta t. So this is nothing but the small change in distance in a small interval of time dt. So this is dx dt. Now delta x, from this we can write it as integration dx, which is nothing but integration of the distance, which is nothing but the change in velocity with time. So this is vt dt. So we have integrated this from the time t1 to t2. So in this way we can write an expression for the change in displacement over a time interval of t1 to t2. Now instantaneous speed is nothing but the magnitude of the instantaneous velocity. So we can represent it as modulus of v of t. Now instantaneous acceleration is the acceleration at any particular instant of time during the motion of the particle. So as we know, acceleration has been defined as the rate of change in displacement. So similarly, instantaneous acceleration a of t can be written as limit delta d tending to 0, delta v dt, delta t or dv dt. So from here if we try to find out delta v, it is nothing but at times t or the integration of that. So delta v can be written as integration of dv, which is equal to integration of at times dt over the interval t1 to t2. Now when we try to write down the average values of any parameter, let us try and recall the average value that we find out for any function f of x. So for any function f of x, the average value can be written as integration f of x dx from x1 to x2 over the change in displacement during that particular interval. So which is x2 minus x1. Now the same thing can be done or used to define different parameters like average velocity or average acceleration. Let us see how we can do that. So here we have the formula for the average velocity. Average velocity v bar is equals to integration vt dt from t1 to t2 over t2 minus t1. So recall for function function f of x, we can write this as integration f of x dx x2 minus x1 from x1 to x2. So what is the difference that we see here? The difference is we are integrating now over time. So the limits are including time. And this is the change of position. Here we have integrated over time. So this is the change in the time interval. Now using position function xt, we initially got dx can be written as v of t dt. So we can simply replace v of t dt by dx in the above relation. So we replace this and we get v bar as equal to integration t1 to t2. In place of v of t dt, we are writing it as dx and the denominator is t2 minus t1. Now what is this basically? When we are integrating dx from time interval t1 to t2, it is nothing but the position at the time t2 difference or minus the position at the point t1. So this is nothing but the change in position of the particle, which we represent by delta x. And this is the change in time, which is represented as delta t. So we get average velocity v bar as equal to change in displacement over the change in time. Time for helpers. The average velocity between any 2 points A and B on an xt graph is the slope of the line segment joining those 2 points. It is path independent. So we have a particle moving from the point A to the point B. Now during motion, the particle could be following any path. It could be following a straight line path, it could be following a curved path or a zigzag path. So independent of the path followed by the particle, the average velocity of the particle in moving from A to B can be found out very easily by finding out the slope of the line segment joining those 2 points. So if we are drawing a line segment AB, which is joining the initial and final positions of the particle, then the slope of this particular line will give us the value of the average velocity. So this is a very good method which we need to take into account while solving numericals. Now average speed, again the same definition using the expression of a function. This is integration from t1 to t2, modulus of dx. This indicates the magnitude of the distance over the time interval t2 minus t1. Similarly, average acceleration can be written as a bar, which is equal to integration t1 to t2, a of t dt over t2 minus t1. Now as you can see here, a of t is nothing but change in velocity. Acceleration can be defined as the change in velocity. So in place of a of t, we have written dv dt times dt. So this ultimately ends up into integration from t1 to t2 dv over t2 minus t1. This is how we can define average acceleration. Now, the small difference between one dimension and two dimension definitions is that you have to remember that two-dimension vector equations are just a combination of two one-dimensional vector equations. Now, velocity and acceleration, to be remembered, they are nothing but vectors. And in one dimension actually, there is no need for any formal notation, but whenever we are into two dimensions, we need to mention vectors or the directions. Now position vector, for any particle or a body which is moving in a plane where we are concerned only with the x and y components, the position vector can be written as vector r equals x I cap plus y j cap. These are the unit vectors along the x and y directions. So it is as if the particle is moving in the xy plane. We have a point at which we need to find out the position vector, that is given by vector r, say. This point, the coordinates of this point are x and y, which means that when the particle is at point P, the horizontal distance covered is x, while the vertical distance covered is y. So this is the thing that we are dealing with. So we have the unit vector along x direction as I cap and the unit vector along y direction as j cap. So we can write the position vector r as equal to x I cap plus y j cap. I cap and j cap basically give the directions of the vectors. Velocity vector is nothing but change in the position vector. So v is nothing but dr dt. Ultimately what we get here is ddt of x I cap plus ddt of y j cap. So ddt of x I cap is I cap times dx dt, which is nothing but vx, and vy can be written as dy dt. Now acceleration vector, we can write it similar to this expression. In place of r we have vector a, and in place of x we have the x component of the acceleration, which is ax, and in place of y, we have the y component of acceleration, which is ay. And to remember that acceleration is nothing but the change in displacement. Sorry, the change in velocity. So, vector A can be written as dv dt. So, from here if we try to write down the components ax and ay, ax is nothing but, you take this as an analogy, you have vector A equals vector dv dt. So, the x component ax will be ddt of vx and the y component ay is equal to dvy dt. So, if we are asked to find out the magnitude of the velocity or the speed, it's nothing but modulus of vector v, which is equal to square root over the components in the x and y directions, that is square root of vx squared plus vy squared. This is all about the vectors when we are talking about a plane, motion in a plane. This is all about when we are talking about motion in a plane. Now, whenever we consider the case of 3 dimensions, what basically changes is we have to add a third component to it, which is the z component, or the k cap part is to be added to it. Now, acceleration, to conclude, acceleration vector, it has got 2 components. One, the parallel component of acceleration, and the second, the perpendicular component of acceleration. So, the parallel component, the tangential acceleration, is that which can change the magnitude of the velocity vector, while the radial acceleration, a perpendicular, that can change the direction of the velocity vector. Now, let us look at some special cases in this regard. When we have a perpendicular, the z component of it, as 0 and a parallel, the z component of it, as not equal to 0. So, the radial acceleration being equal to 0 means that there is no change in the direction of motion of the particle. So, this is nothing but the case of rectilinear motion. Now, for the second case, when a parallel is 0 and a perpendicular of z is not 0, then a parallel 0 means that there is a change, there is no change in the magnitude of the velocity vector, or we can say that for this particular case, the magnitude of velocity vector does not change, or velocity is constant here. What changes is the direction of motion. So, saying that velocity is constant would not be quite good, because what we are trying to mean by this is that the magnitude of the velocity vector remains constant, but anyways the direction of motion could be changing, which will not allow the velocity as a whole to remain constant. So, this is in fact the case of uniform circular motion. Now, the third case, if both the radial and the tangential accelerations are not 0. So, this is the case of a complicated motion. For example, when we consider the motion of a projectile, or the motion, or we can consider the case of non-uniform circular motion. So, let us look into uniform and non-uniform circular motion in a bit more detail. Let us try and first look at the position vectors in terms of polar coordinates. We have talked about the expression of the position vectors in terms of x and y components, that is the rectangular components. Now, what if we are to change the coordinate system? We are to shift to the polar coordinate system. So, what are the changes basically that take place here? So, for the plane, in case of a plane, or when we are concerned with the rectangular components of position vector, then we had written vector r as equal to x I cap plus y j cap, considering motion in a plane. Now, what changes here in polar coordinates is that in place of x we have r cos theta, and in place of y we have r sin theta. Now, in terms of time, theta is replaced by omega t plus phi. Phi is the phase change or the phase angle, and omega is the angular velocity. Angular velocity, to recall, it is the change in angular displacement and given by d theta dt. So what we do here is that we replace theta by omega t plus phi. Now velocity can be found out as the differentiation of the position vector. So vector v of t is nothing but d dt of vector r of t. Now if you look at this expression, when you are differentiating with respect to time, this is the variable only that you are to consider. R comes out common, cos of omega t plus phi. This is basically, you have to think of cos. Let me try to show this to you. This is d dt of cos of omega t plus phi, which is actually, you can write this as dd of omega t plus phi cos omega t plus phi times or multiplied by d dt of omega t plus phi. So just look at this. This is just like the previous one. Only thing is that we have made the variables similar. The ddx of cos x, which is nothing but minus sin x. So for this part, if we are differentiating, we get minus sin x, where this is x is omega t plus phi, and ddt of omega t plus phi is a constant. Differentiation of a constant is 0. We are left with ddt of omega t, which is nothing but omega. So this is what we get for this, ddt of cos of this. So minus omega sin omega t plus phi. We are to similarly proceed for differentiation of time with respect to cos. When we consider cos, it is nothing but sine of omega t. So ddt of cos omega t, cos we have already discussed. We are trying to talk about sine omega t plus phi. This is nothing but cos of omega t plus phi. So let me change this. Omega t plus phi. So this is to be replaced here. Now have a look at this. We have r taken out. R is a constant. It has been taken out. And what we got here is this. This is minus omega sine omega t plus phi. So see, minus omega sine of omega t plus phi, I cap remains, r has been taken out being a constant. And for the second part, we have r and omega comes out again. When we are doing this, omega will again come out and we have r omega common, and cos, for sine we have cos of omega t plus phi. So just have a look at the magnitude here for velocity. It is nothing but root over x square plus y square. So what is x here? R omega into minus sine of omega t plus phi. This is x, and y is again r omega cos of this. So when we are doing x square, square root over x square plus y square, what comes out is square root of, show this, r square omega square. You can take this as common, and for sine we have square of that. We are left with sine square omega t plus phi plus cos square omega t plus phi. So this part will give us sine square theta plus cos square theta, which is 1. So we are left with only r omega. So you can see the magnitude of the velocity vector is equal to r omega. Now similarly, we can find out for the acceleration vector, vector a of t is equal to vector ddt of vector v of t. Now we have v of t here. If we differentiate this again with respect to time, what we are going to have is minus r omega, and omega comes out from here, so minus r omega square, and ddt of sine is cos. So we are left with the cos term, and for the second part we again have r omega and another omega coming out from here, and then cos of omega t plus phi, differentiation of that gives us minus sine. So that minus sign can be taken out as it appears in both the terms. So ultimately we are left with minus r omega square, and this part, if you see, it is nothing but vector r of t, which we have got here. We have written this. So this is vector a of t, which is equal to minus omega square r of t. Now you can find out the magnitude of vector a of t as well. So you can see this is nothing but vector a of t, which is, sorry for this, the modulus sign has to be carefully given. So this is minus omega square, and talking about the modulus of vector r of t, if you see the modulus, the magnitude, it is nothing but r square. Okay. So you can write this. From here this is root over r square cos square omega t plus t phi plus sine square omega t plus phi, which comes out to be 1, and then we have square root over r square, which is r. So this comes out to be r. You can do this here, and ultimately we are left with this expression. Now we get to conclude some things from here. Let's look at that. So you can see from here, we ended up at that a of t is equal to minus omega square r of t. Now what is it that you can find out or you can say about it? Just look at this. So what we have here is omega square is always a positive quantity. Why? Square term. Square term, always it comes out to be positive. So this tells us that the acceleration vector is in fact antiparallel because of the negative sign. It's antiparallel to the position vector, and it always points inwards towards the center of the rotation. So here the acceleration is called centripetal acceleration, and the magnitude accordingly, avoiding the negative sign, as whenever we are talking about magnitude, we do not include the sign. So we can write the magnitude of acceleration vector as omega square r. If you substitute omega, we had got v is equal to r omega. So omega can be written as v by r, and we substitute the value of omega here. We get the magnitude of the acceleration vector as v square by r. Now talking about uniform and non-uniform motion, whenever we are talking of a body which is moving in uniform circular motion with constant speed, its acceleration actually is not zero. This is because the particle, whenever it is moving in a circular path, at every point of motion, the direction of motion is changing, which causes the velocity to change, and change in velocity means that the acceleration is not zero. Now, what is non-uniform motion? Whenever a particle is moving in a circular path but with non-constant velocity, then we say the motion is non-uniform circular motion. For example, if we are considering the motion of a roller coaster in a vertical circle, so that in that particular motion, what happens is that the acceleration has got both radial and tangential components, and as a result, the direction of the acceleration is also not exactly towards the center of the circle. So this is the thing, the radial acceleration and the centripetal acceleration both are equal to v square by r, and the tangential acceleration in fact can be calculated from the change in velocity with time. So this is all about the theory on kinematics whenever we are talking about APC. but you can always refer to APC videos, AP1 videos on kinematics for details into the theory. Thank you.